Hi children, welcome. Welcome to another chemistry class. In this class, we will be discussing some important questions from the chapter Solid State Chemistry. That is the first chapter of 12th standard syllabus. Ready? Can we start? First question. A simple question. The vacant space in BCC lattice unit cell is. Vacant space is asked. So how much space is occupied? What is the packing efficiency of BCC? All of you have studied, but still I am telling you. The packing efficiency in BCC crystal is equal to volume of particles divided by volume of unit cell into 100. So what is the volume of the particles? How many particles are there in BCC? All of you know BCC system is 8 particles at the corners and 1 particle in the body center. So the rank of BCC is at, all of you know, 8 particle at the corners, it is 1 by 8 into 8 equal to 1. And 1 particle in the body center, that is 1. So 1 plus 1, 2. 2 is the effective number of particle per unit cell, right? So what is the volume of the particles? Assuming particles to be spherical and the radius of particle to be taken as r. So it is 2 into 4 by 3 pi r cube divided by volume of the unit cell. Edge length of unit cell, assuming it to be a, so it is a cube into 100. Now once you know the, see what are the terms? R means radius of the particle. A means volume of the, A means edge length of the unit cell. So A cube means volume of the unit cell. So all of you know packing efficiency in BCC is equal to volume of particle divided by volume of unit cell into 100. Volume of particle means the volume of effective number of particles. How many effective number of particles? 1 by 8 into 8 equal to 1 and 1, so it is 2 particles. So it is 2 into 4 by 3 pi r cube divided by a cube into 100. Now if you get a relation between a and r, the calculation is over. All of you know for BCC system, what is the relationship? The body diagonal root 3a is equal to 4r. You have learnt. Root 3a is equal to 4r, right? So what is a in terms of r? A in terms of r will be 4r by root 3. Substitute that, you get 2 into 4 by 3 pi r cube divided by 4r by root 3 the whole cube into 100. You have worked out, but I am just reminding you. You have worked out. I am just reminding you, right? And what will be the packing efficiency you are going to get? Hope you remember. In BCC it is 68%. Upon calculating, you will get 68%. Simple calculation you can work out. You will get 68%. What is our question? Our question is vacant space is the question. What is the vacant space? That is the question. So 68% is occupied. That means 32% is vacant. So the answer is 2. Is it clear? Yes? Okay. Next question. Packing efficiency is 68%. Therefore, vacant space is 32%. Okay, next. The correct statement regarding defects in crystal solids. Frenkel defect is a dislocation defect. Frenkel defect is found in halides of alkaline metals. Schottky defect have non-effect on density of crystalline solids. Frenkel defect decreases the density of the crystallines. The fundamental statements from the Frenkel defect, Schottky defect. And you are easily been able to understand. The correct answer is first choice itself. It is a dislocation defect. How it becomes a dislocation defect? It is arising because of high difference between the ions. Usually a small cation and a large anion, and thereby the cation are displaced from its actual site. That is what the cause of dislocation. That is the Frenkel defect. First choice itself is the wrong statement. Frenkel defect is correct statement. Frenkel defect is a dislocation defect, and that is our answer. What is the point with the second choice? Frenkel defect is found in alkaline metals. No, these are the quite common examples where you find Frenkel defect. Zinc loss, zinc sulfide, AgBr, AgI, AgCl. Refer the textbook. You have seen that. Third choice, Schottky defect have no density, no effect on density. You know, it causes decrease in density because it is missing of equal number of cations and anions. So there is a decrease in density, you have learned. And option D, Frenkel defect have no effect on density. Frenkel defect decreases the density. It is wrong. So this is wrong, this is wrong, this is wrong. Frenkel defect does not cause a decrease in density because it is not a case where the particles are missing. It is not a case where the particles are missing. Particles are there in the crystal itself, but not in the original site. It is actually misplaced. So there is no decrease in the density of the crystal. Density remains the same. I think it is clear. Next question. In calcium fluoride, having the fluorite structure, the coordination numbers of calcium and fluoride ions are. You have learned in the classes what is fluorite structure. In fluorite structure, say for example calcium fluoride. How it is coming? Calcium forms FCC. The cation forms closed packed system. And anions are available in the tetrahedral voids. Anions are present in all tetrahedral voids. So how much FCC if it is? Z is equal to 4. So there are 4 particles, that is cation. Now, how many tetrahedral voids? Tetrahedral voids will be 2 into n. N is equal to 4. N is equal to 4. Therefore, it is 8 tetrahedral void where all you have fluorine. So, calcium 4. Fluorine 8. So, that is the character. There are 4 calcium, and 8 fluorine. Now you see each calcium surrounded by 8 fluorine and each fluorine surrounded by 4 calcium. So what is the coordination number? What is the coordination number? CaF2. There are 4 calcium and there are 8 fluorine, and that's how the formula comes out to be CaF2, 1:2. That's how the formula comes, CaF2. Now, each calcium surrounded by 8 fluorine. So, coordination number of calcium is 8. Each fluorine surrounded by 4 calcium as it is in the tetrahedral void. So, the coordination number of fluorine is 4. And the answer is 8:4 coordination. And go for the first choice. 8-4 coordination. Now think about how comes in anti-fluoride structure. You have learned. What comes in anti-fluoride structure, say for example Na2O, where oxygen makes FCC and cation present in all tetrahedral voids. Check out. Okay? Just opposite. That is why anti-fluoride. So rock salt structure, zinc sulfide structure, fluoride structure, anti-fluoride structure, spinal structure, inverse spinal structure. These are all the advanced level topics which you need to learn from the chapter. Okay, next. That is about the description regarding the fluoride structure. Next one, which is incorrect statement. You want to know incorrect statement, option A. Option A is a correct statement, that is a metal deficiency defect. Option 2, density decreases in case of crystals with the Schottky defect. Just now we have commented, true statement. NaCl, insulator, silicon, semiconductor, silver conductor, quartz, piezoelectric. True statement. All of you know, quartz is a piezoelectric substance. What is meant by piezoelectric? A crystal which is getting polarized upon applying a mechanical stress or vice versa. That's why it is used in quartz watches. For getting an accurate measurement of the timing, we are using that piezoelectric quartz-like material in watches, right? What is the property piezoelectric? Upon applying a mechanical stress, there will be electrical polarization or vice versa. Okay. Now NaCl, please make a note on to solid matter. Solid NaCl is insulator, while in the molten state or aqueous solution, it can conduct electricity, and that is called the electrolyte. The rest 2 points you know. So all the 3 are true means answer should be option 4. Frankel defect is favored in those ionic compounds in which size of cation and anion are almost equal. That is wrong statement, and that is our answer. It is not almost equal. When there is a large difference in the size of ions, it causes Frankel defect. Usually a small cation with a large anion where the cations are misplaced into the vacant site causes Frankel defect. Okay, children, next. So the answer is fourth statement. Fourth statement. Next one. Iron exhibit BCC structure at a room temperature. So BCC structure at a room temperature above 900 degrees Celsius, it transformed to FCC structure. So above 900, it is changing to FCC. The ratio of density of iron at room temperature to that at 900 degrees Celsius. So we need to find the ratio of density. That means dBCC divided by dFCC, because it is asked d room temperature by d 900 degrees Celsius. D room temperature means BCC, D 900 degrees Celsius means FCC. This is what you need to know. And I am sure all of you remember density D is equal to Zm by Na cube. Zm by Na cube. All of you know that, right? So for BCC, FCC, what will be Z? And that is what the point of discussion in this case. So let us examine how that can be calculated. Keep this in mind and this is what we need to find out. This is what the primary equation which we need. Okay, so what do? You just apply on the situation. D is equal to Zm by Na cube. Right? So what do you want? D BCC by D FCC, that is Z M by NAA cube for BCC divided by Z M by NAA cube for FCC. This is what you want. So what is Z for BCC? 2. All of you know. M, there and here, same. Z for FCC, 4. So Z for BCC, 2. Z for FCC, 4. And NA will get cancelled. Now what is the next one? A for BCC. All of you know what is A for BCC and A for FCC. A for BCC, what is the relation? What is the relation? All of you know. It is root 3A is equal to 4R. And A for FCC, what is the relation? It is root 2A is equal to 4R. So keep these two relations in your mind. Here A will be 4R by root 3. Here A will be 4R by root 2. So here A is equal to 4R by root 3. 4R by root 3, the whole cube. We are talking about A cube. We are talking about A cube. So A cube in the first case, 4R by root 3 whole raised to cube, 4R by root 2 whole raised to cube. Simplify. Keep on simplifying. Simple mathematical analysis to get the answer. What the answer? 3 root 3 by 4 root 2. You will get the answer 3 root 3 by 4 root 2. Like that. Okay, children? Fine. So which choice? Option 1. Option 1 you get. Simple cancellation. You will get your answer. 3 root 3 by 4 root 2. A question where there is a definite possibility of committing some mathematical mistakes. Of course, application mistakes. So do it carefully. Do it 2-3 times. Many times such a question was repeatedly coming. Okay, important question. Next. A compound is formed by cation C, anion A. The anion form hexagonal closed packed lattice and cation occupies 75% of octahedral void. The formula of the compound is. Another simple question. You have C and A. A anion forms closed packed arrangement. This is forming HCP, closed packed arrangement. So let this be one particle. That means N is equal to 1. And then tetrahedral void is equal to 2. And octahedral void is equal to 1. As all of you know, octahedral void will be N. Tetrahedral void will be 2N. I am taking number of particle of A which forms closed packed system as 1. Suppose I am taking A equal to 1. That is N is equal to 1. Tetrahedral void will be 2N, that is 2. And octahedral void will be N, that is 1. Is it clear? So, tetrahedral void if it asked 2. Octahedral void if it asked 1. Now, C is said to be available in 75% of octahedral void. The cation present in 75% of octahedral void. That means 3/4 octahedral void is occupied by cation. So number of cation will be 3/4. Number of cation will be 3/4 of 1. So number of cation will be 75% means 3/4. So cation 3/4, anion 1. Over. You get your answer. C 3/4 and A 1, that is C3A4. C3A4. And the correct answer will be option 2. C3A4 is the correct answer. So anion forms closed packed arrangement. Take anion 1. Then how many octahedral void? Number of octahedral void will be same as the number of particles which forms the closed packed system. So if there are n particles, there will be n octahedral bonds. Now out of that, 3/4 is occupied by cation. So C is, A is 1, C is 1 into 3 by 4. That is 3 by 4. So what is the formula? C 3 by 4, A 1, that is C3A4. Okay? Next. C3A4. Next. An element has a body-centered cubic structure with a cell edge length given atomic radius. Asked for atomic radius. You've been asked for atomic radius. Cell edge length A is given, and we are talking about BCC. Very simple question. It is root 3A is equal to 4R. Therefore, R is equal to root 3A by 4. R is equal to root 3A by 4. Root 3A by 4. Root 3A by 4. Option 4 is the correct answer. Option 4 is the correct answer. Direct question. Next. In the hexagonal prism-shaped unit cell of HCP structure of metal, number of atoms per unit cell is, number of atoms per unit cell in HCP. HCP, how the arrangement comes, all of you know how the arrangement comes in HCP. How is the arrangement happening? It is one hexagonal arrangement in one layer, and it forms, you have seen in the textbook and all, and you know the arrangement well. And how is the particles coming? How is the particles coming? One here, one here, one here, one here, one here. There are 7 particles on top, and there are 7 particles at bottom, and there are 3 particles over here. And that forms layer A, layer B, layer A, and hope you remember AB packing is called HCP. AB packing is called HCP, right? And what is the contribution of each particles? What is the contribution of each particles? That too you know. The contribution of this particle will be 1/6th contribution. Sorry. Yeah, 1/6th contribution, isn't it? 1/6th contribution, isn't it? Because there will be unit cell 3 in the same layer and 3 on the top layer. 1/6 contribution. How many particles are there? 1/6 into, there are 6 over the top, 6 at the bottom. I forgot to give one particle here, right? I forgot to give one particle at the bottom. So it is 1/6 into, how much? 1/6 into 6 over the top, 6 at the bottom. So it is 12. You get 2 particles. Now this is a face center particle. All of you know, half into 1 over top, 1 at the bottom, half into 2. That is 1 particle. Then how much? These 3 particles are entirely available inside the unit cell. So it is 3 particles. So 2 at the corners, 1 in the face center, and 3 in the body center, a total of 3 plus 3. 6 particles are there in the unit cell. There are 6 particles inside the, effective number of particles for HCP. How it is 6? The contribution at the corners being hexagonal, the contribution at the corners 1/6. How it is 1/6? See, around this unit cell there will be 3 unit cells, one here, one here. And similarly on top also. So if you take this particle, it will be a common point of 6 unit cells. So for 1 unit cell it will be 1/6 contribution. So 1/6 into how many corners? How many corners? 6 corner on top, 6 corner at the bottom. So it is 12 corners. So it is 1/6 into 12, 2 particles. Now face center contribution as usual, half. So half into 1 here, 1 here. So half into 2, 1 particle. And these 3 particles in the entire unit cell itself. So it is 3 particles. So it is 3 plus 2 plus 1, 6 particle, and the answer is option Which one? Option C. That is the correct answer. Right? Wow. Here, if you want to know how that arrangement is coming, it is perfectly given as a diagram. You see, this is the particle arrangement. This is the space filling model of HCP. And this is the open model of HCP. I was talking about this particle. The contribution is 1 by 6. I am talking about this particle, which is contribution 1 by 6. And then I was talking about this particle, the contribution is half. I was talking about this particle, the contribution is half. And then I was talking about these three particles, the contribution full three particles, these three particles. So it will be 1 by 6 into like this. There are 6 at the top, 6 at the bottom. So it is 1 by 6 into 12, 2. Half into 2, 1 top, 1 bottom, 1. And 3 particle inside. I think it's a beautiful diagram to make you know how the arrangement is there in HCP. Is it? Fine. So the answer is option C. Next question. A ferromagnetic material among the following is, those who have gone through NCERT, the famous example of ferromagnetic material, various transition elements along with the oxide of chromium. This is the answer. This is the answer, all of you know. CrO2 is a ferromagnetic material. CrO2 is a ferromagnetic material, while option A, Fe3O4 is ferrimagnetic in nature. Option C, GaAs, that is simply a doped semiconductor, while MnO2 is anti-ferromagnetic. The examples are there in the textbook. You have to learn and equip yourself to answer such a question, simple, direct question. Next one. Total number of planes of symmetry for a cube is. Total number of planes of symmetry for a cube is. See, that is regarding planes of symmetry, and there can be questions: how many axes of symmetry, how many elements of symmetry for a cubic system. For a symmetric cubic system, how many elements of symmetry it can have? How many plane of symmetry? How many axes of symmetry? How many total elements of symmetry? My dear children, there are 23 elements of symmetry in a cubic system. There are 23 elements of symmetry in a cubic system. How comes 23 elements of symmetry? Can we have a look at? Can we have a look at? This too is a advanced level question. I mean, a bit outer level question from the syllabus point of NCERT, which definitely you must learn. You must learn. You see, what are the planes of symmetry? You can see, simple. If you take a cubic system, don't you find a plane that will cut the cube into two equal half, and that plane is called a plane of symmetry. It's beautiful diagrams available here, which will make you know what are the planes of symmetry. There is a horizontal plane of symmetry. There is a vertical plane of symmetry. There is another vertical plane of symmetry. So these three planes are of similar type. So you can take it as 1, 2, 3. And now the planes are diagonal planes. That are diagonal planes which cut the cube into two equal half. Right? You see, another diagonal plane of symmetry, another diagonal plane of symmetry, another diagonal plane of symmetry. Here another one, and this, hope you understand, through the other three diagonals. How many? See, the diagonal planes, how many are there? Very simple to know. There are 12 edges. It is passing through the edges. You see that? It is passing through the edges. How many edges are there? There are 12 edges. One plane forms how many edges? 2 edges. So total how many planes? 6 planes. How is that? You see, this edge and this edge form a plane. So how many total edges are there in a cube? There are 12 edges. 2 edges form one plane. So there are 6 planes. How 6 planes? 1, 2, 3, 4, 5, 6 planes. While the other, they are not through the edges. They are not through the edges. They are cutting the cube into two equal halves which are passing through the axial points. Is that clear? So these three one type, these six one type. So the answer for what our question is, planes of symmetry. Planes of symmetry. There are 9 planes of symmetry. There are 9 planes of symmetry. Now let us have a talk on axis of symmetry. Axis of symmetry. Here we have the diagram. Even though that question is not a part of this question, I'm telling you that suppose a question comes on that, let's have a look at this. This is axis of symmetry. You see one axis passing through. There are 3 axes, x, y, z axis. Let this be x axis, let this be y axis, let this be z axis. There are 3 fourfold axis of symmetry. There are 3 fourfold axis of symmetry. What is meant by this fourfold axis of symmetry? Fourfold axis of symmetry means, that means 360 divided by 4. That is, if you rotate by 90 degree, you will get a same arrangement. That is what n axis of symmetry. That is what Cn axis of symmetry. Cn, here it is C for symmetry. What is that C for symmetry? That is fourfold axis of symmetry. How do you understand that? 360 by 4. How much? 90 degree. If you rotate by 90 degree, you will get the same configuration. That is what the meaning. Okay, there are 3. One through the x-axis, one through the y-axis, one through the z-axis. And now there are threefold axis of symmetry. There are threefold axis of symmetry. What is threefold axis of symmetry? 360 divided by 3. 360 divided by 3. How much it is? 120 degree. If you rotate by 120 degree, the configuration will repeat. If you rotate through an axis 120 degree, the configuration will repeat. What is that axis of symmetry? Very simple to know. It is through the body diagonals. It is through the body diagonals. You see, these two opposite corners are passing through that axis, and that is body diagonal. How many body diagonal are there? There are 4 body diagonal, and there are 4 threefold axis of symmetry. So fourfold axis of symmetry, there are 3 axis of symmetry. Threefold axis of symmetry, there are 4 axis of symmetry. And finally, there are twofold axis of symmetry. There are twofold axis of symmetry. What is twofold axis of symmetry? This is twofold axis of symmetry, which is passing through the edge centers. Which is passing through the 2 opposite edge centers. How many edges are there? 12 edges are there. There are 12 edges. How many axes of symmetry will be there? There will be 6 axes of symmetry. So this is 3, and this is 4, and this is 6. A total of 6 plus 4, 10 plus 3, 13. There are 13 axes of symmetry. 13 axes of symmetry. There are 9 planes of symmetry, 13 axes of symmetry, 9 planes of symmetry. So total 22. I told you initially there are 23 elements of symmetry. So 13 axes of symmetry. How 13? 6 twofold symmetry, 4 threefold symmetry, and 3 fourfold symmetry. So a total of 22 now. Which is 23rd one? It is center point of symmetry. It is called the center point of symmetry. That's a point of symmetry. So 9 planes of symmetry, 13 axes of symmetry, and 1 point of symmetry called the center point of symmetry. Okay, a total of 23 elements of symmetry. 23 elements of symmetry. How 23? 9 plus 13 plus 1. 9 plane of symmetry, 13 axis of symmetry, 1 point of symmetry. I think it is clear. It's an important question. Okay, next one. The substances formulated as Cl2, Ba2, Ca2, Cu3O10. That is a mixed oxide. That's a mixed oxide. Hope you simply understand. Behave as a superconductor at a very low temperature. Exactly. There are several such mixed oxides which can act as superconducting materials at low temperatures. Superconductivity first observed by Camerlin-Ons in mercury at 4 degree. And later on, several materials were developed and the industry is quite moving fast, very fast. And there are so many advanced materials nowadays available which are in low temperature superconducting material and high temperature superconducting. High temperature means relatively high, right? So, low temperature superconducting materials were very famous at the older ages, but then we were trying to get high temperature superconducting materials in the advanced materials. The inventions are going on. And this is a superconducting material which can act as superconducting at very low temperatures. All mixtures of metal oxides are superconductors at low temperatures. No, that is wrong. So that is correct. This is wrong. Assertion correct, reason wrong. Option C is the correct answer. We can't expect all metal oxide to be superconducting at low temperatures. Okay. Yes. Next question. Answer is option C only. Other factors remaining the same. When the edge length of cubic unit cell is doubled, the density becomes. So all other remain the same. Edge length is doubled, density will become. Simple question, right? D is equal to Zm by NaA cube. All other remaining the same. We are talking about this and this. So what is the point? D proportional to 1 by A raised to 3. When you are doubling this, it is 2 raised to 3. It will become 1/8 times. Option C. Option C gets reduced to 1 by 8, the original value. Option C. Okay, next. A metal crystallizes into two cubic phases, that is FCC and BCC, whose cell edge length are given. Cell edge length are given. The ratio of their densities. Ratio of their densities. So once again, DFCC by DBCC, that is what asked a similar question which we did earlier. So what is the relation? D is equal to Zm by NaA cube. D is equal to Zm by NaA cube. Right? What do we want? We want DFCC by DBCC. So how is going to be the relation? 4 into M by NaA cube, whose edge length are 4 cube, divided by 2 into M by NA 3 cube. So NA cancels. 4 by 4 cube, 2 by 3 cube. It is 4 by 4 cube divided by 2 by 3 cube. So it is 4 by 4 cube divided by 2 by 3 cube go to top. So that's over. P means D. P means D. So it is D proportional to X by A cube. X means what I written Z. Z. So over 27 by 32. You get 27 by 32. Option D. 20 simple mathematical. Similar question we did. Similar question we did. You can exercise on that. And that shows the importance of that kind of question. Okay, next. Following materials can be arranged in the order of size of energy gap between filled valence band and empty conduction band. Filled valence band and empty conduction band. The energy gap for filled valence band and empty conduction band, I am sure you remember. For insulators, the energy gap will be very large. For conductors, it may be overlapping, and for semiconductors, it can be very small gap. So what is the point of arrangement comes? This is how it comes for conductors. This is valence band. Sorry. This is conduction band. And this is valence band. So valence band and conduction band will be overlapping somewhat for conductors. That's why they are excellent conductors of electricity. While for semiconductors, all of you know it may come like this. There is a very small energy gap for semiconductors. What about insulators? Insulators, there will be a huge gap. There can be a huge energy gap, forbidden energy gap between the valence band and the conduction band for insulators. So here an insulator means a non-metal. Here an insulator means non-metal. So definitely sulfur is maximum. Sulfur is maximum. Therefore A and D out. Now after sulfur, it will be germanium. Answer is option C. After sulfur, it will be germanium. All of you know germanium is a semi-conducting material. So sulfur is a non-metal. So the energy gap is large. And then it will be germanium, which is semiconductor, a small energy gap, while calcium, iron, etc. will be very close or overlapping. Okay, so the answer is option C. Zinc oxide becomes yellow on heating and white when cooled. This is due to zinc oxide becoming yellow on heating and white when cooled. This is due to metal excess defect. Metal excess defect due to extra cation. Metal excess defect due to extra cation. When you heat zinc oxide, some oxygen will escape. There will be a reorganization in the crystal and excess zinc will be trapped in the vacant sites and electrons will be trapped in the nearby interstitial site forming F centers. It is metal excess defect due to extra cation. Metal excess defect due to extra cation. Option B. Okay, next. In an ionic solid, cations A occupy 50% of tetrahedral voids produced by the cubic close packed arrangement of anion B. You see, we have A and B. This forms CCP. And let that be one particle. Then number of tetrahedral void will be 2. Number of octahedral void will be 1. Already we have discussed. So B forms CCP close packed arrangement. So let the number of atoms be 1. Let the number of atoms be 1. Okay, that means N equal to 1. Then number of tetrahedral void will be 2 times N. And number of octahedral void will be 1. And here A cation occupy 50% of tetrahedral void. 50% of tetrahedral void. So tetrahedral void is 2 and 50% of that. That means A is 1, B is 1 and the formula is AB. Formula is AB, option B. So number of atoms of A, 1. Number of atoms of B, 1. So B forms CCP. So let it be one particle. Then number of tetrahedral void will be 2. 50% of that occupying A. That means A will be 1. So A1, B1, AB. Next. Square close packing coordination number. Square close packing coordination number is 4. Square close packing coordination number is 4. Each particle surrounded by 4 particles. Reference CRT. The diagram is available. Hexagonal close packing. It's asking in one layer, I believe. Yes, one layer. In one layer, square close packing, the coordination number is 4. In one layer, hexagonal close packing, coordination number is 6. Next. Silver chloride has rock salt structure. If the nearest silver and chlorine atoms are at a distance x, the nearest AG distance will be. See, rock salt structure. You know how comes rock salt structure. I'm just showing the rock salt structure arrangement along a face. Along a face where you can find the particles are available like this. The particles are available like this. Where this is chlorine and this is Ag. All of you know. This is how the arrangement coming in rock salt structure. Chlorine forms corners and face center, FCC arrangement, where sodium available in all octahedral void. Where comes the octahedral void? Edge centers. So like that, AgCl is coming. At a corner, there will be chlorine, and at octahedral void means edge centers, there is Ag coming. So this is Ag, this is chlorine. What is given here? The nearest silver chlorine distance is x. It is given here. This distance is given as x. And what is asked? The nearest Ag distance is this distance they are asking. So if this is x, that means this is x. What is this? Root 2x. See, this is x. This is x. What is this? Root 2x. Apply Pythagoras theorem, you know. Isn't it? Isn't it? This is x. This is also x. So what is this? What asked for is nearest Ag distance. So this square is equal to this square plus this square. So x square plus x square is equal to this square. So 2x square is equal to this square. So that is equal to root to 2x. So the answer is option C, root to 2x. Root to 2x. Okay. Yes. Next. Root to 2x. Aluminium crystallizes in CCP lattice. The edge length of unit cell given. The number of atoms of aluminium in 1 centimeter cube of the element is. So edge length given, CCP lattice. The crystal structure given CCP, edge length given. We want to know the number of atoms of aluminium in 1 centimeter cube of aluminium. Okay. So commenting CCP means number of atoms of aluminium in 1 unit cell will be 4. CCP. So number of aluminium atoms in 1 unit cell, it will be 4. Okay. Now What is the volume of one unit cell? You can calculate. What is the total volume given? You know. It's given. Total volume asked for the number of aluminum atom given. Volume of one unit cell you can calculate. So number of unit cells you can get. Into 4 will be the number of aluminum because each unit cell contain 4 aluminum. Each unit cell contain 4 aluminum. How much volume they are asking? Given. What is the volume of one unit cell? You can calculate. So A cube, you will get volume of one unit cell. Okay, the total volume divided by volume of one unit cell, you will get the number of unit cells. Into 4, you will get the number of aluminum atom. Okay, yes. So volume of one unit cell, you can calculate. Number of unit cells in 1 centimeter cube, you can calculate. Each unit cell contain 4 aluminum atom. Therefore, total number of aluminum atom, it is the number of unit cells into 4, you get your answer. Check whether you get that or not. Option C. Some 9 something into 10 power 22. Is it clear? Next question. Percentage void in the unit cell of diamond is. Percentage void in the unit cell of diamond is. You know what is the arrangement of diamond? What is the arrangement of diamond? Diamond is something similar to zinc sulfide structure. The structure of diamond is similar to zinc sulfide structure. So diamond structure is similar to zinc sulfide structure, where sulfur go for FCC and zinc available in alternate tetrahedral void. While in diamond, carbon atom present in all positions of sulfur and in all positions of zinc. All positions of sulfur, that means FCC, that means 8 corner and all 6 face centers. There is carbon. Alternate tetrahedral void, there is zinc, and that position also carbon. Okay, so that is the arrangement of diamond, carbon in diamond. That means you can see the packing efficiency, volume of carbon atom into 8, because there are 8 particles in the unit cell. How it is 8 particles? How it is 8 particles in the unit cell? There are FCC, sulfur, 4 sulfur, alternate tetrahedral void. Number of tetrahedral void is 4, n equal to 4 means number of tetrahedral void is 8. Alternate tetrahedral void means half into 8, 4 particle. So there are 4 sulfur, 4 zinc, all position occupied by carbon. Therefore, number of carbon atom is 8. Okay. So volume of carbon atom per unit cell, it is 8 into 4 by 3 pi r cube. Volume of carbon atom in the unit cell, it is 8 into 4 by 3 pi r cube divided by a cube. Divided by a cube, where a is the edge length. Where a is the edge length. Right? Now, 1/4 body diagonal is equal to 2r. 1/4 body diagonal is equal to 2r. That means, see, if you take a cubic arrangement, here there is a carbon, and you know there is a carbon here. This is the tetrahedral void. This is the tetrahedral void. 1/4 distance from the corner, that is the tetrahedral void. Therefore, these 2 particles in contact, this distance is nothing but 1/4 body diagonal. 1/4 body diagonal, that is equal to 2r. See the 2 particles in contact. This distance is 2r, and that is nothing but 1/4 body diagonal. So 1/4 body diagonal is 2r. What is body diagonal? All of you know, root 3a. Body diagonal is root 3a. So body diagonal is root 3a, 1/4 of that. 1/4 of that. That is 1/4 root 3a. This is equal to 2r. Therefore, r is equal to, r is equal to root 3a by 8. R is equal to root 3a by 8. R is equal to root 3a by 8. Now substitute here r, or you can substitute a. A is equal to how much? 2r by, 8r by root 3. A is equal to 8r by root 3. That also you can substitute. By substitution, you get the packing efficiency. You will get packing efficiency 34%. Packing efficiency of carbon in diamond, it is 34%. What is asked here is percentage void. So the percentage void will be 66%, option C. Okay. So understand, the arrangement of carbon in diamond, it is similar to zinc sulfide arrangement. How is zinc sulfide arrangement coming? All sulfur in the FCC arrangement and zinc in the alternate tetrahedral void. What is the position of tetrahedral void? 1/4 distance from the body diagonal. And all these sulfur zinc present is equal to carbon in diamond. So this is carbon, all the corners carbon, all the face centers carbon, and alternate tetrahedral voids there is carbon. This is the tetrahedral void. I am not drawing the entire structure. So there is a carbon in the corner and there is a carbon in the tetrahedral void. So this distance is 1/4 body diagonal. What is body diagonal? Root 3a. 1/4 body diagonal, root 3a by 4. That is equal to 2r. And that will give you the packing efficiency of diamond. If you get packing efficiency of diamond, you get the void. Packing efficiency we are calculating 34% and the void will be 66%. Is it clear? Next. NaCl doped with the 10 power minus 3 mole percentage of strontium chloride. The number of cation vacancies is. Number of cation vacancies is. My dear children, all of you know, when 2 NaCl missing from the crystal, 1 strontium will come. When 2 NaCl removed from a crystal, 1 strontium will replace. All of you know. So that is the fundamental idea you must know. 2 Na plus, when out from the crystal, you get 1 strontium introduced in the crystal. That means 2 sodium out and 1 strontium comes. That means the 1 position will be replaced by strontium and 1 will remain a vacancy. 2 sodium out. Sodium, 2 positions. 2 are missing. 1 strontium comes. That means there will be 1 vacancy. So the position of 2 sodium become vacant. And in that 2 position, out of 2 position, 1 position strontium will occupy. That means 1 position will remain vacant. So number of strontium in is equal to 2 sodium out. That is equal to 1 vacancy. So number of strontium is equal to number of vacancies. Number of strontium is equal to number of vacancies. NaCl dropped with 10 power minus 3 mole percentage of strontium. So strontium is 10 power minus 3 mole percentage strontium. That means 100 mole, there is 10 power minus 3 mole strontium. Therefore, 1 mole, there is 10 power minus 3 divided by 100 mole strontium. That is 10 power minus 5 mole strontium. That will be 10 power minus 5 into Avogadro constant, number of strontium. That is 6 into 10 power minus, 6 into 10 power 18 strontium. This is the number of strontium. That is the number of strontium that is introduced. That means that is the number of vacancies. Number of vacancies is equal to number of strontium. Number of vacancies equal to number of strontium. The number of strontium is this much. Number of vacancies equal to same. Answer is option B. Answer is option B. Let me repeat. 10 power minus 3 mole percentage. Percentage means out of 100. So out of 100 mole, 10 power minus 3 mole strontium. Out of 1 mole, 10 power minus 3 by 100, that is 10 power minus 5 mole strontium. That means how many numbers into Avogadro number? That is this much of strontium introduced. Okay. Number of strontium in is equal to number of vacancy. How is that? When 2 sodium removed, 1 position occupied by strontium, 1 position remain vacant. So number of strontium coming is equal to number of vacancies. Next question. Option B. Next. A solid XY has rock salt structure. The radius X plus is 100 picometer. Radius of anion will be. Radius of anion will be. All of you learnt for a rock salt structure, it is octahedral arrangement and the radius ratio comes out to be R plus by R minus is equal to 0.414 to 0.732. This is the radius ratio range. Right? That means the range comes out to be R plus by R minus is equal to 0.414 the minimum range and R plus by R minus is equal to 0.732 the maximum range. That means R minus can be R plus by 0.414, that is one range, and R minus can be R plus divided by 0.732, that is the next range. These are the limiting range of anion. That is the limiting range of anion. And in that range, hopefully there is one choice coming. In that range, hopefully one choice is coming. You see, R plus, that is 100. 100 by 0.414 is 241. This is one range, 241. 100 by 0.73 to 137. So the R minus value should be in between these two. And the answer will be option D, 220. Option D, 220. Okay. So please learn the radius ratio range. R plus by R minus, 0.155 to 0.225. Trigonal system. Triangular system, 0.225 to 0.414, tetrahedral system, 0.414 to 0.732, octahedral system, 0.732 to 1, cubic system. Learn that. Next. The schematic alignment of magnetic moment of different substances. See the diagram available in the textbook, which is the last portion of the chapter, finishing with that point. Paramagnetic, diamagnetic, ferromagnetic, antiferromagnetic, ferrimagnetic. Hope you remember. So option 1, choose the wrong statement. 1 is ferromagnetic, that is true. 2 is antiferromagnetic. Down, up, down, up, down, up, that is true. 3 is ferrimagnetic. 3 is ferrimagnetic. Down, down, up, down, up, down. Yes, that is ferrimagnetic. 4 is antiferromagnetic. Up, down, down, up, down, down. No, this is not antiferromagnetic. That is also ferrimagnetic. Fourth one is ferrimagnetic. So what is ferro? All in one alignment. All dipole in one alignment. Ferro. The dipoles aligned alternately. Antiferro. The dipole aligned parallel, anti-parallel in unequal number. Ferri, ferri. Okay. So the answer is D. It is ferrimagnetic. Next question. The above diagram represent F center. Above diagram represent F center. That is metal excess defect due to anion vacancy. Metal excess defect due to anion vacancy. F center. Next. And that electron trapped is called F center. Number of unit cells present in 1 gram NaCl is. Number of unit cells present in 1 gram NaCl is. My dear children, NaCl makes rock salt arrangement. NaCl go for FCC system. Chlorine go for FCC and sodium present in all tetrahedral voids. Chlorine 4 and sodium 4. Chlorine 4, sodium 4. It is actually 4-4 combination. That means 1 unit cell contain 4 NaCl. 1 unit cell contain 4 NaCl. That means 1 mole unit cell contain 4 mole NaCl. 1 mole unit cell means Avogadro number of unit cell contain 4 into 58.5 gram. 4 mole NaCl, 4 into 58.5 gram. Therefore, 1 gram, how many unit cell? That is a question. 1 gram, how many unit cell? That is a question. How many unit cells? How many unit cells? It is Na divided by 4 into 58.5. That is 6.023 into 10 power 23 divided by 4 into 58.5. If you take 58.5 equal to 60 somewhat, 60 cancels, you get 10 power 22, 1 by 4, that is 0.25 into 10 power 22, 2.5 into 10 power 21. Option B will be the answer. Option B will be the answer. Simple calculation, you will get the answer as option B. Avogadro number divided by 58.5 into 4. Simple calculation, take this as 60. 60 with the 6, 1 by 10. That is 10 power 22 by 4. That is 0.25 into 10 power 22. 2.5 into 10 power 21. You can easily calculate option B. Okay, next question. A certain sample of wustite is found to have a composition iron 0.9, oxygen 1. The percentage of Fe3 plus in the total iron content is. Percentage of Fe3 plus in the total iron content is metal deficiency defect. Metal deficiency defect. You see, the charge of total anion must be equal to that of the cation. And here it does not happen like that. So what happens is, some of the Fe2 plus will be converted to Fe3 plus to neutralize the system. So how many Fe3 plus are there? That is a question. Simple, no? How you calculate that? How you calculate? You see, iron 0.9, oxygen 1. That means iron 90, oxygen 100. Oxygen 100 means minus 2 into 100, 200 negative charge. 200 negative charge. Okay, now 90 iron should give 200 positive charge. Oxygen giving 200 negative charge. So 90 iron, 100 oxygen give 200 negative charge. So 90 iron should give 200 positive charge. Then only it can neutralize. I mean the charge can be equal. So what happens? What happens? Suppose it is plus 2. Suppose iron is plus 2. Suppose iron is plus 2. Plus 2 into 90. You get only 180. You get only 180 positive charge. That means there is a deficiency of 20 positive charge. Okay, so 20 Fe2 plus must be converted to Fe3 plus. So please understand, out of 90 iron, 20 will be Fe3 plus and the remaining 70 will be Fe2 plus. Now you please work out. 70 into 2 plus, it is 140. 20 into 3 plus, that is 60. So positive 140 and positive 60, you get plus 200 charge, and that is compensated. Now you see that it's the simple mathematics. 100 oxygen, 2 minus 200 charge. 90 iron should give plus 200 charge. What will be the composition? Out of 90 iron, 20 will become Fe3 plus, 70 will remain 2 plus. Is it clear? So what is the fraction of Fe3 plus? 20 out of 90 into 100. 20 out of 90 into 100. You will get 22%, option C. A question which you need to practice at least some 2-3 examples. There is a highly probable question. Okay, next. An alloy of copper, silver, gold. Copper atom FCC. Copper atom makes FCC. So Cu will go for FCC means 4 Cu. Silver at edge center. Silver at edge center. Edge center means 1/4 into 12 edges. There will be 3 silver. So 4 copper, 3 silver, and the gold at the body center. Gold at the body center. Gold at the body center means 1. So 4, 3, 1. Which choice? Option B. Copper FCC. So it is 4. How 4? 1/8 into 8 equal to 1. And 1/2 into 6 equal to 3, 4. Silver at the edge centers. Edge center, what is the contribution? 1/4 contribution. How many edges? 12 edges. 1/4 into 12. 3 particles. And copper in the, gold in the body center. Next. Both the Schottky defect and Frenkel defect observed. KGBR. AGBR is a typical example which perform both Schottky defect and Frankel defect. One example you should never forget. Okay, the size of silver and bromine comfortable in that range that it can perform both the Schottky defect and Frankel defect. Next. Conductivities of semiconductors. Refer the textbook. Go through the range of conductivity shown by conductors, insulators, semiconductors. A direct question from the textbook. Option A. This is the range of semiconductors, conductors and insulators. Refer the text. Option A. Oxide ions are in close packed arrangement and a metal ion occupy 2/3 of octahedral void. Formula of the oxide is again the same type of question which we did. Metal and oxygen. Oxygen forms close packed arrangement. So let this be 1. Then number of tetrahedral void will be 2. Number of octahedral void will be 1. And it is placed in 2/3 of octahedral void. M is present in 2/3 octahedral void. Octahedral void is 1. So it is 2/3. M 2/3. Oxygen 1. That is M2O3. Option A. Option A. Option A. Oh, that was the last question. Option A. Right? So, that is some important questions. We have tried to incorporate some additional questions which are on the higher level side also in this discussion, which definitely a possibility of coming questions, and it is based on the experience what we find in the previous exam papers. Try to solve as many questions as possible on this kind. Okay. So we will meet with another chapter, another beautiful set of questions in the next class. Okay. Bye. See you. Take care.